Hi, hello ib2 students, welcome for next video lesson about black body radiation, or general about radiation. We'll focus on black body radiation. Okay, I hope you are prepared to the lesson. You have pen, pencil, calculator, and of course your tsokos. Yes? So please now open your tsokos on page number 329. 329. Okay, and read carefully this page about thermal energy transfer, about conduction, convection, and radiation. Okay, so this is something like revision of methods of heat transfer: conduction, convection, and radiation. Okay. You have, let's say, 5 minutes. Stop video, read just this page. Okay, you have 5 minutes. After 5 minutes, please turn video again. Okay, so after 5 minutes, I hope you remember from middle school what the conduction is. Yes, conduction is a method of heat transfer by kinetic energy of the molecules. If you have an object which is heated up in one side, yes, then molecules are vibrating faster and colliding with neighboring molecules, and these collisions or this kinetic energy pass through the object. So conduction occurs mainly in solids where density is high and the molecules are very, very close one to another. Okay? Second, convection. What the convection is? Convection occurs mainly in liquids and in gases when hot region mix with cold region. So basically, if you have in the room the hot region near radiator and cold region in the rest part of the room, then this hot air moves up and displaces cold air, and cold air moves in different place. So mixing by moving or displacing of the molecules. Okay, and radiation, something we have to focus today. Radiation is the method of heat transfer by electromagnetic waves, mainly in infrared region, mainly because it depends on the temperature of the object, and this is only one method of transfer of heat when heat can pass as the energy through the vacuum. Okay, so today we'll be talking mainly about radiation. Yeah. Okay, so topic: black body radiation. This is tsokos page number 330. So topic is black body radiation. So first of all, let's look. If you have an object, then amount of radiation, okay, depends on the temperature. If you have two objects, let's say the cold one and let's say the hot one, then both, and cold and hot, okay, emit energy in the form of radiation, but amount of radiation emitted by cold is much less than amount of radiation emitted by hot. Okay, so hot object emits more energy in the form of radiation, in the form of electromagnetic waves, than a cold one. Is it clear? Okay. So what is a black body? If I give you a relation between temperature of the object and amount of radiation emitted by the object, we have to explain term black body. A black body is a perfect emitter or perfect absorber. Okay, so right, point number one, black body is a perfect emitter or perfect absorber. Okay, what does it mean? It means that if you illuminate a black body, okay, by a light, then the black body will absorb all of the radiation. Okay, will not reflect the radiation. Will absorb all of the radiation. What is very important, if black body has a very high temperature, is not black, is bright. Is it clear? So black body in high temperature emits all radiation, or emits energy in the form of radiation. Okay? So if question is what is a black body, your answer is it's a perfect emitter or perfect absorber. Okay? There is a parameter which differs black body on other real objects. Remember that black body is a theoretical object. Is it clear? A theoretical, a kind of model. So a parameter which distinguishes between black body and real objects is something known emissivity. So I give you definition of emissivity later, but now if emissivity of the object is equal to 1, then it is a black body. Okay? If emissivity of the object is less than 1, then object differs on black body. So if emissivity of the object is, let's say, 0.9, it is almost black body. Okay? If it's 0.8, it is the emissivity 0.9 is closer to black body than emissivity which is equal to 0. Okay, when emissivity which is equal to 0, then object that doesn't emit energy. Just this. Is it clear? Okay, but let's focus on this. Point number 1. Black body is perfect emitter or perfect absorber. Okay? So now I need this picture. Okay. And next you can write power radiated by the object as a next point. Power radiated by the object. And so point number 2, power radiated by the object. Okay, in your physics data booklet, you have equation, okay, for power emitted by the object at a given temperature. So amount of radiation radiated by the object depends on 4 parameters. Depends on a parameter called emissivity, okay, here. I was looking for the constant. So A is emissivity. Okay, depends on the constant. Okay, called, sorry. No, well, it's opposite. Okay. The constant is known as a Stefan Boltzman constant. Okay, depends on the surface area of the object. And depends on the absolute temperature to the power of 4. Okay, so T is temperature in Kelvin. Okay, so Stefan Boltzmann constant has a value of, here is written, 5.67 times 10 to the power of minus 8. 5.67 times 10 to the power of minus 8. And Stefan Boltzmann constant has a unit of watt per square meter per Kelvin to the power of 4. Okay. And this power radiated by the object is known as a Stefan Boltzmann law. Okay, so let's look. If you have an object of given temperature and the given shape, you can calculate surface area of this object. Then you can calculate also power radiated by the object. So amount of joules emitted in the form of radiation in each second. This emissivity, okay, this is a number which from the range from 0 up to 1, and if emissivity is equal to 1, then object radiates as a black body. So write somewhere, if emissivity is equal to 1, then object behaves as a black body. Okay, so by using this equation, we can also define emissivity, but it will be next point. Okay, so let's do one exercise related with this equation. Okay, let's write example 1, and your task will be to find power radiated by the sun. So find power radiated by the sun. Okay, and of course I have to give you something. Radius of the sun, Rs, is equal to, let's find, it is 6.96 times 10 to the power of 1, 2, 3, 4, 5, and 3 zeros because kilometers, so times 10 to the power of 8 of meters. Okay, remember that the sun is a sphere, and let's assume that sun behaves as a black body. Sun radiates as a black body. Okay, and I forgot about one very important parameter. You have to know temperature of the sun's surface. So next data, temperature of the sun is 5800 of kelvins. Okay, so please stop video for a moment. Use Stefan Boltzman law to find power radiated by the sun, assuming that sun emits energy as a black body, and it's a sphere of radius 6.96 times 10 to the power of 8, which has a temperature at the surface 5800 kelvins. Okay, stop video, you have 5 minutes. After 5 minutes we'll check your solution. Okay, I hope you have something. So you have to use this equation, okay, where emissivity is equal to 1, because black body has emissivity equals to 1. This constant is 5.67 times 10 to the power of minus 8. Okay, surface area is area of the sphere 4 pi r squared, so times 4 times pi times the radius, which was 6.96 times 10 to the power of 8, 6.96, yes, times 10 to the power of 8, but this 696 times 10 to the power of 8 is squared, okay, times 5800 to the power of 4. Unfortunately, my calculator still doesn't work. I hope that your result is correct. I can try because we have something like this. Finally, it will be 5.67 times 4 times pi times 6.96 to the power of 2 times, I'm going to write 5.8 to the power of 4 times, and now we have 10 to the power of minus 8 times, here we have 10 to the power of 8 to the power of 2, which is 10 to the power of 16, and here I have 10 to the power of 3 to the power of 4, so 1000 to the 10 to the power of 3 to the power of 4 gives 10 to the power of 12. Okay, now I can use calculator, my powerful calculator, 5.67, okay, times 4 times pi times 6.96 times again 6.96 because it's squared times 5.8 times 5.8 times 5.8 times 5.8 8, which is 3.9 times 10 to the power of 6. And here we have minus 8 plus 16 is plus 8, and here plus 12 is plus 20. So finally 3.9 times 10 to the power of 26 of watts, and it sounds good. Okay, I hope you have the same answer, or otherwise my answer is the same as here. Okay, so what if you have an object, yeah, which is hot, okay, placed in the cold surroundings, but this cold is not absolute zero. Okay, in this situation, of course, object emits radiation, so loses energy due to the Stefan-Boltzmann law, but also absorbs it from the surroundings. Amount of absorbed is of course much more less because surroundings has a less temperature. So in this case, total power of the object or total power emitted by the object is difference between power which is emitted and power which is absorbed. Okay, so finally in the situation when object is placed in the surroundings, then let me move it, you can calculate power by using double Stefan-Boltzmann law. So you have to to find this power, you have to multiply emissivity of the object times this times area of the object times temperature of the object to the power of 4, yes, minus emissivity of the surroundings times this times surface area of the object, because object absorbs, times temperature to the power of 4 of the surroundings. So here we have object, here we have surroundings. Is it clear? Okay, so now next point we can explain what the emissivity is. So point number probably 3. Okay, point 3, emissivity. Okay, so emissivity has a symbol of E, is a number from 0 to 1, it has no unit, but emissivity can, let's look, if you have this Stefan-Boltzmann law, let me write it again. Okay, then when emissivity is equal to 1, we have black body, and for black body power emitted can be written as sigma a t to the power of 4, because for black body emissivity is equal to 1. Okay, so power emitted by black body is equal sigma surface area times temperature to the power of 4. So let's compare two objects. A real object which has emissivity, so PR real is emissivity sigma a t to the power of 4, and a black body, a theoretical object of the same temperature, which has power as sigma a t to the power of 4. Okay, so if these two objects have the same surface area and the same temperature, then there is only one difference between power in emissivity. You see this? So we can write that power of real object, okay, is emissivity times power emitted by black body of the same surface area and the same temperature, or we can write this in the form of power emitted by real object to power emitted by black body. Okay, and this equation is definition of emissivity. Okay, so it's a ratio between power emitted by real object and power emitted by black body of the same area and the same temperature as real object. Okay, so emissivity is a ratio between power emitted by real object and power emitted by black body of the same surface area and the same temperature. Okay, please copy this. Okay, so let's look. If a real object emits the same amount of radiation as a black body, then what happens? Then it is a black body because it has emissivity equals to 1. Okay, so please copy this as a point number 3, emissivity. Okay, here in SOCOS, on page number 330, you have emissivities of some objects. Okay, black body has emissivity equals to 1, ocean water has emissivity equals 0.8, ice has very small emissivity equals 0.1. Why? Because ice reflects radiation, not absorbs. Dry land has emissivity of 0.7, land with vegetation has emissivity equals 0.6. Yes, so you see that it depends on the surface. Okay? Right, point number 4, next one, Wien's displacement law. Wien's displacement law. Okay, so the Wien's displacement law is about frequency or wavelength of emitted radiation. Okay, and Wien's displacement law says that there is one specific wavelength called peak wavelength for specific temperature in which object emits a lot or most of energy. Okay, so Wien's displacement law says that this maximum wavelength, maybe not maximum wavelength, wavelength of maximum intensity, okay, multiplied times temperature in kelvins is equal constant 2.90 times 10 to the power of minus 3. Okay, and this constant has a unit, Kelvin times meter. This is not kilometer, Kelvin times meter. Okay, so what does it mean? It means that for each temperature we have specific wavelength for which, in which amount of energy emitted is the biggest possible. Okay? Open your SOCOS on page number 331. Yeah? And you have some graphs. What does it mean? Okay, first of all, if you will create a graph how intensity of radiation depends on the wavelength. Wait, first of all, short revision what the intensity is. Remember, intensity is power over surface area. So intensity is power emitted or absorbed by 1 squared meter of the area. Okay? Then you have to obtain a kind of curve. Okay, and you can see that there is one specific wavelength called lambda max, but this is not the maximum wavelength. This is wavelength for which intensity is a maximum. Okay, and due to this law, due to the Wien's displacement law, this maximum lambda depends on the temperature. Okay, so I'm going to create another curve, the blue one. Okay, what is the difference between blue one and the black one? In the case of blue, we have another lambda max, the bigger one, okay, but smaller maximum intensity. Now, what does it mean? It means that the blue curve has less temperature than black curve. Okay, high temperature, small temperature. So let's look. If temperature of the object is bigger, then of course object emits more radiation due to the Stefan Boltzmann law. Power or intensity is proportional to the temperature to the power of 4. Okay, so object emits more radiation than object with less temperature, and due to this Wien's displacement law, object also has different color. The radiation which is emitted the most has shorter wavelength. Is it clear? Okay. So again, if we have object of higher temperature, then it of course must emit more, and color of the radiation is different because lambda maximum is shorter. Okay, and this something is called Wien's displacement law. Okay, I'm going to present, maybe not present, let's write example. Let's imagine that you have two objects, yes, and curves of intensity versus lambda are presented on the same graph. First object has a curve like this, okay, and second object has a curve like this. And let's imagine that values are given. That intensity of first object is, let's say 1, doesn't matter, and second object has intensity of, let's say, 0.4, but both have the same value of lambda for this peak. Okay, what does it mean? What is the difference between these two objects? Okay, these two objects must have the same temperature. You see? Let's look on Wien's displacement law. Objects have the same temperature because have the same lambda. Lambda times temperature is equal constant. So we know that object, let's name black line object number 1 and violet line object number 2. So we know that temperature of first is the same as temperature of second. Is that clear? Okay, and let's look. If first object has intensity bigger than other, then there is only one solution. If objects have the same temperature and different intensities, it means that the second object has smaller emissivity. So emissivity of second must be less than emissivity of first, because second emits less radiation, okay, per square meter than first object, and both have the same temperature. Remember, the law, Stefan Boltzmann law, says that emissivity times constant times area times t to the power of 4 must be constant. Area is the same because intensity is per square meter, per 1 unit of surface area. You see difference between this graph, graph A, and this graph, graph B? In first graph, we have displacement of lambda max, which means that objects must have different temperatures. In second, we have the same lambda max, which means that objects must have the same temperature. Okay? If there is the same temperature and another intensity, it means that there must be another emissivity. Okay? So let's write example 2, and let's use this Wien's displacement law, okay, and calculate the peak lambda, so lambda max for sun. Okay, so write example 2 in this point, use Wien's displacement law and find lambda max for sun. Okay, so lambda max times temperature is equal 2.9 times 10 to the power of minus 3, this is constant. And for sun, temperature I gave you in the last exercise is 5800 kelvins. Okay, so all you have to do is to divide 2.9 times 10 to the power of minus 3 by 5800 kelvins, of course. Do this. No, it's exactly. Okay, I have obtained 5.0 times 10 to the power minus 7 of meters, or you can write this as 500 nanometers. What does it mean? 500 nanometers is a yellow color. Okay, this is why sun is visible as a yellow. It emits all radiation, all wavelengths due to this curve. Okay, but the peak is for 500 nanometers, which corresponds with yellow color. So we can see all from short, so violet, to long, red, but the biggest intensity is for yellow. So this is why the visible color of sun is yellow. Is it clear? And due to the Wien's displacement law. Okay, so let's conclude this lesson. Yeah, we were talking about the black body. So black body is an object which is perfect emitter or perfect absorber. We're talking about Stefan-Boltzman law, which says that power emitted is emissivity, Stefan-Boltzmann constant, surface area, and temperature to the power of 4. And for black body, where emissivity is equal to 1, we can write this equation as sigma a t to the power of 4. Okay? We're talking also about intensity. Intensity is power over area, so we can write that intensity of the object is emissivity sigma t to the power of 4, or emissivity for black body is sigma t to the power of 4, which means that both and power and intensity both are proportional to the fourth power of temperature in Kelvin scale. Is that clear? Okay, and we're also talking about Wien's displacement law, which says that the wavelength of maximum intensity multiplied by temperature is constant, and this constant is equal to 2.9 times 10 to the power of minus 3. Okay? So let's finish the lesson. Your homework is to read carefully Tsokos, page number 330, 331, plus example on page number 332. So read 330, 331, plus read and try to understand, and understand example on page number 333. Okay, 332, sorry. Read 330, 331 and example on 332. Okay, so thank you for watching. I hope you like this lesson. Be prepared next time. I have to organize a kind of assessment test quiz. I don't know form yet, but I will think about this during the weekend. Learn physics, stay at home, and goodbye.